All right, now we're going on to hydration of an alkyne. Let's start with something that you know already. So an alkene, so we have added mercury, right? So we have oxymercuration and demercuration, two steps. The first step, adding mercury, so you form a three-membered ring mercurinium ion, right? And then water attacks, so you get water right here. You get mercury on this side, on the let's substitute carbon, and then remove the mercury. So we do demercuration, add sodium borohydride. All right. So alkene use mercury. Alkyne, guess what? Ta-da! Mercury, same thing. You know. But the product, so the initial product, got a double bond there, Marconi-Corp right here. So add on to the small substitute carbon. You know. For alkene, you don't have a double bond right here. But for alkyne, yes, you have a double bond right here. Adding mercury and an OH, just remove one double bond. So you get another. Sorry, just remove one pi bond. Just you got another pi bond in here. All right, so then you're gonna get an enol product. We'll talk about this in a bit, and then tautomerize to the ketone. Okay, and we have to talk about the tautomerization right here. All right, all right. So real quick about tautomerization. You will learn about this in more detail in organic chemistry too. If you take it, if you don't, just look at right here. All right, tautomers is a constitutional isomer that rapidly interconvert via the migration of protons. So basically, proton moves from one spot to another. These are constitutional isomers. They have the same molecular formula, but different connectivity. So protons here, double bond here, double bond here. Okay, and tautomerization is a process of transfer from one isomer to another, basically, and it can be triggered by using acid as a catalyst or a base as a catalyst. Either one works. All right. All right, so look at this compound real quick. So we call it enol. All right, why do we call it enol? Because it got an alkene and an alcohol next to each other on the same carbon. So this carbon here, alkene, and the same carbon got an alcohol. So en and ol. So alkene and alcohol. So we call enol. And enol is not stable. It will tautomerize in acidic or basic solution, become a ketone. We have an enol form and ketone form. All right. So enol can also do aldehyde, same condition. Basically everything's still the same. Right. Two carbon chain, one carbon chain. You can get either ketone or aldehyde. Depends on the structure, basically. All right. So what you have to be able to do is to draw the mechanism that convert enol to ketone form or enol to aldehyde. They have the same mechanism. Right? There are two ways to do that. Use acidic solution or basic solution. All right, start with acidic. So acid catalyzed tautomerization. So we have an enol form, adding an acid. This is an acidic solution. The first step is going to be a protonation for sure because it's strong acid. All right. So you get a carbocation right here. You can draw the resonance structure. Another one right there. All right. And now you can see this guy right here. This real strong acid. Right, if you check the pK negative 2.7, yeah, look back to the pK table, really strong acid. The next step going to be, well, strong acid, go deprotonation. Every time when you say strong acid, either protonation or deprotonation occur, you get a ketone. And the acid is coming out like that, so that's why we call an acid catalyzed tautomerization. So that acid is acts as a catalyst, add on to the reaction at the beginning, comes out at the end, never get consumed. Okay. All right. Base catalyzed tautomerization. So we add a base into the solution. So, for example, hydroxide is floating around. So adding a base, what does base do? Opposite of an acid. So deprotonation. Acid do protonation, base do deprotonation. All right. So deprotonation, you get negative charge on oxygen. Right. And you can draw the resonance structure there. That's kind of weird arrow. So this is supposed to go all to the bond right there. This should be go to the bond. All right. And I got a negative charge right here. That's your nucleophile, and then protonation. Right. In this case, for this structure we got an aldehyde. Right. For this structure we got a ketone. Okay. Because this carbon got two alkyl groups on it. This carbon of alcohol got only one alkyl group on it. This is hydrogen. All right. All right. So basically, what I want you to see right here, if you do tautomerization in an acidic solution, the step going to go protonation, deprotonation. If you use a base in basic condition, deprotonation comes first and then protonation later. So it's reversed basically. They are exactly the same thing, but just reverse order. Okay. All right. Now go back to the hydration. So Marconi-Corp hydration of alkyne use mercury, same thing, mercury sulfate. All right, from an enol. And then this guy will tautomerize to ketone. All right, we're going to talk about this step right here. You don't need to know this mechanism. I just want to show you how it works. Similar, very similar to alkene. Nucleophilic attack. Oh, by the way, so this is mercury sulfate. It's an ionic bond. So mercury is floating around as an ion in the solution. Okay, so you get mercury got on it, and you got carbocation right here. All right, we don't do the mercury doesn't get on the other carbon because the other carbon right here you get a primary carbocation which is less stable. All right, mercury attack. Just like in alkene, so you form three-membered ring there, highly unstable. Water comes in, which is you add water in there too. So there's a solution. Attack on the more substitute carbon. Markovnikov right there, right? So water gets on to the more substitute carbon. All right, the confusion is right here. So that's why I tell you, you don't need to know this. Strong acid, deprotonation. Make it neutral. And then, all right. Now, this mercury will be removed by doing this nucleophilic attack, proton transfer, this protonation onto this compound. You get a carbocation right there, and then mercury leave, just like, you can draw the resonance structure here, and then mercury leave the molecule. Look like an enol. That is an enol from double bond here and OH here, which will tautomerize to ketone. All right. So that's my point is you don't need to memorize all this. I don't care. All you have to be able to do is the tautomerization on here from enol to ketone. But I just want to show you why it goes Markovnikov, because this species right here, same thing. Not tertiary, three-membered ring and water attack them on the more substitute carbon. Markovnikov orientation. Okay. All right. Let's talk about this anti-Markovnikov using boron, just like alkene. Let's talk about this on the next video.